I don't have any copies with me. Anyway, any questions from yesterday? Yesterday, we laid a foundation for thinking about line positions, strengths, and shapes. We dealt with diatomic molecules, introduced the role of quantum mechanics in constricting our choices of energy levels and transitions. So today, in the first lecture, we're going to look at what happens when the molecules are bigger. Let's look at polyatomic spectra, and we're going to confine ourselves to the rotation vibrational aspects of this. Do that in the first hour. In the second hour, we'll introduce the equation of radiative transfer, which brings in the methodology that we use to calculate an absorption coefficient. And then in the third hour, we'll begin talking about line shapes. Remember, we talk about line positions, line strengths, and line shapes. Okay, so what happens when we go from diatomic to polyatomic? And what happens is you first have to classify the molecule. So it'll fit into one of four classifications, and that will guide us through the path of how we deal with the rotational and the vibrational spectra. So in the way of review, remember the energy for rotation is given with a capital F, function of only one quantum number J, units of wave numbers, which is 1 over wavelength. If we confine ourselves to a rigid rotor, we have a very simple expression where B is the rotational constant, unique to that molecule, depending only on its moment of inertia. With the selection rule, this delta J is 1. And line position is given by a simple expression. So if you neglect this distortion term, which is small, tends to be very small, the interpretation is pretty simple. Now, what happens when we go to 3 or more atoms? So the first thing you do is we go back to our classical mechanics, and we establish the center of mass, and we establish the 3 principal axes. They're known as the principal axes, and the definition of the principal axes is such that there's no so-called products, moments of inertia. So there's always in any system, there are 3 axes that can be defined orthogonal to each other, which are the principal axes. So we find the center of mass, whatever this object is. We typically first then define what's called the A-axis. It's called the unique or figure axis. It's usually an apparent symmetry axis. And then B and C are orthogonal. And we then evaluate the moments of inertia about each of these axes. And then the molecules are classified depending upon these values or relative values of these moments of inertia. Here's the 4 classifications that we typically use: linear, symmetric top, spherical top, asymmetric rotors. Here's some examples of linear molecules: CO2, acetylene, OCS. So those are like sticks, thin sticks with points, masses along those sticks. So they're linear. Symmetric top is the case where, and that's the case where IB equals IC because the orthogonal axes B and C are degenerate. We say that the moment of inertia about the A-axis, which is the axis through the nuclei along the stick, that's the A-axis. The moment of inertia about that axis is very small. It's not exactly 0. Symmetric top, the definition is that the moments of inertia B and C are equal but different than A. And the spherical top is when they're all 3 equal, and the asymmetric rotor is when they're unequal. These are some examples. So ammonia, which I had on my first slide, it's like a 3 things sitting on the floor with one thing pointing up. It's like a tripod. Ammonia. Or methyl fluoride, the same thing, only with the additional atom up here. And boron trichloride, which is in a plane. Those are all examples of symmetric tops. And then there's the spherical top. We use methane as an example. And then there's the asymmetric rotor case, which actually is the biggest category and the hardest category. Water is an example. NO2 is another one. So these first 2, linear and symmetric tops, are relatively simple. The spherical top is not of interest to us because it's not a microwave active, meaning it doesn't have dipole moments that are active. And then the largest category, the hard one, we will defer. And that's typically when we would retreat to a database such as Hydran. So we're going to start simple. We always start simple and then progress. Simple case of a linear molecule, carbon oxysulfide. So here's our linear molecule, and because it is asymmetric, it'll have a dipole moment, and therefore is going to be microwave active. Here's the masses of the atoms. Here, sulfur is the heavy one. Here's the center of mass. The A-axis is along the stick. The B-axis is perpendicular, and then C-axis perpendicular. Typical lengths are of the order of 1 angstrom. And here's some pictures. Let's look at B. This is what happens if we watch the rotation about the B-axis. And C is exactly the same thing, only rotated 90 degrees. So that's what it would look like, and therefore, since it's asymmetric, there would be a dipole moment associated with it. Next level up is called the symmetric top, of which there are 2 types. One is called prolate. This is the case where, here's an example now, like a tripod. This is a case where the moment of inertia about A, the axis, is small compared to the moments of inertia about B and C. So, and if you look at this and study it, you'll realize that the moment of inertia about B and C are equal. So that's the definition of a symmetric top. Here's the example down here in a stick figure. So we have the light hydrogens. Here's the A-axis that's along the vertical axis of the tripod. And we have fluorine of 19, carbon of 12, hydrogen of 1. So you can see that the moment of inertia about the A-axis is small because only the H atoms are moving around, whereas the moment of inertia about B and C are large. So this fits the definition of a prolate symmetric top. There's 2 types, prolate and oblate. The oblate is just the reverse case where the moment of inertia of A is large. So now we have this example down here of boron trichloride, it's called. And so it's in a plane. So the unique axis would be through the center and out of the board. Now you see that the moment of inertia about A is the big one relative to B and C. So there's these 2 categories. They have similar equations, but different trends with the energy spacing for those 2 cases. Spherical top. Best example for a spherical top is methane. Methane is there's like a cube, and then the hydrogens are opposite corners. So it takes a little thinking, but if you think about it enough, you'll find out that it's symmetric. There's no dipole moment. There's no rotational spectrum. We're not going to worry about it anymore. So spherical tops, not a problem. We don't have to deal with it. Asymmetric rotors, this is the most common case. Let's look at water. Water, so 3 atoms can be formed into a plane. Where's the unique axis? This is the axis for which you can obtain symmetry. So the vertical axis A through O means that when I rotate the water molecule around, you can't tell the difference. So that's the unique axis. We call it A. And B and C are perpendicular. So this case is complicated, and we won't address it here, but it's tabulated. Let's go to the simple case now. We're going to try to do the rotational spectra. Here's these linear molecules. OCS, HCN, CO2, acetylene. Now this one is perfectly symmetrical. CO2 is symmetrical. The others are not. So already we can tell that there will be no dipole moment. They won't be microwave active. The energy levels exist, but we can't see them by absorption or emission. Must be asymmetric to have a dipole moment. Isotopic substitution does not change this because, as I told you yesterday, the bond lengths are set by electrical forces, not by the masses. We can go back to the expressions we had before for diatomic. In fact, what we find is that there's no change. The F of J is still BJJ plus 1. Going from 2 to 3 atoms along the stick doesn't change anything. It's still a linear molecule has the same simple result. So the good news is linear triatomics, linear 4-atom molecules, we have the same relations we already have. The interpretation will be the same. The energy level structure will be the same. And one difference will be that there's more masses involved. Therefore, the moments of inertia are going to be bigger. Therefore, the rotational constant is smaller, and the line spacing will be closer. So that's the main thing that you would see in the spectrum. Larger I, smaller B, and therefore smaller line spacing than the diatomic case. Frequently, we'll suppress the lower level J and just call it J double prime, just call it J. Okay, now, so linear molecules, if we, like yesterday, if we decide how would we find out what the lengths and masses of a molecule are, we can use absorption or emission spectroscopy to find B. Each time we do that, we can get one value of I. But we need more than that. depending on how many atoms there are in this system, we may have to use a number of isotopes. And so n-1 isotopes will give us n-1 values of the B. That's what we would need in order to sort out the lengths of this carbon oxysulfide molecule. So with the proper use of, say, 2 isotopes here, you can solve for the 2 lengths, RCO and RCS, if you know the masses. So that's the simple mechanical model that we have. And there's no change from what we did yesterday for the rotational spectrum. The next step is to go to symmetric top. Symmetric top, here's my cartoon. So it's basically like the top you should have seen when you were young. There's a spinning top that precesses around the vertical axis. So it's spinning about its own axis while it precesses around the vertical axis, like a top. Because it's spinning around 2 axes, we have to have 2 quantum numbers for angular rotation. Angular momentum is the key in quantum mechanics. So we actually have to now introduce a new quantum number, which stands for the rotation about this axis. So that's the complication. We're going to have a J. J is typically the total angular momentum. It's still quantized as 0, 1, 2, 3. K is the angular momentum about the unique axis. That's the unique axis. And it now can have any value plus or minus up to J. K cannot exceed the total. If the total is J, then K can only reach that value. But it can spin around either clockwise or counterclockwise. Therefore, the angular momentum about A can be of different signs. Now, what about the allowed, by the way, plus and minus have the same energy. It's just that there's a different orientation. So now that means that there are 2 J plus 1 possibilities of K for each J. So for example, if J is 1, then K could be 1, 0, or minus 1. So there's 2 J plus 1 possibilities of K for each J. So things are getting a little more complicated, but not too bad. Now, because the angular momentum is quantized, so that's really the place you start. Angular momentum is quantized. That leads to the energy being quantized. So now we sum up the angular momentums from quantum mechanics, and we find that that sum of these squared components is J plus 1 H squared. Remember, we had just the square root of J plus 1 when we did I omega. Now we have the new requirement that pertains to the A axis only. So now we have J and K that specify the problem. Now the energy levels now depend on J and K. And so here's our rigid rotor term, and here's the term that corresponds to the rotation here. So you can go through the algebra and find this is the new expression depending now on 2 quantum numbers. Notice that it's K squared, so it's independent of the sign. And it depends on the difference between A and B. What are A and B now? A is just that moment of inertia term, with moment of inertia in the denominator. So it depends on the magnitude of A and B. Now B is what we call the rotational constant, so now A is the rotational constant for rotation about the A axis. So it's just a question of the relative values of A and B. And that's why we're back to the oblate prolate case. What about the selection rules? Delta J remains 1. Delta K is 0. Why is that? Well, there's no dipole moment for rotation about that axis. So it kind of follows physically that we keep the same quantum number constriction, J of 1, but delta K is 0. So since there's no dipole moment for rotation about that unique axis, no change in K occurs. Now, so what does that mean about the line positions? So the positions of the lines in frequency units are, as usual, the difference between the upper state and lower state. And what do we get? Exactly the same thing we've had before. So the symmetric top doesn't really complicate our lives that much at this level, at the rigid rotor level. It becomes more complicated when we correct this. So the symmetric top then is when these 2 moments of inertia are equal but different than A. Now when we introduce non-rigid rotation, now this is when the complication comes in. So instead of having the simple result down here that we had before, this term right here, we have to add some new terms. And that means that when we look at the frequencies, the line positions, the expression looks a little more complicated depending upon how big these d values are. So the implication of non-rigid rotation, it just complicates things. So that where there was going to be individual, only one line position, there may be a cluster of lines that are closely spaced. So we'll look at an example. Here's this methyl fluoride example. There's a tripod. Here's the value of B in wave numbers. And here's the distortion terms. So these are known. These are numbers that you can look up. Now, if you look at J of 20, for example, so that J squared is 400, and then look at the magnitude of some of these terms, you would find that they're pretty small. So generally, they can be neglected, unless you have high precision. So here's our spacing of the lines, 2B, which would be 1.7 wave numbers for different J's. That means all of the K's would be lumped together under that line. But there are actually 3 lines for J of 2 for 3 values of K. So in fact, if you could expand this dramatically, you would find that there are 3 lines here instead of 1, although their spacing is of the order of 10 to the minus 4 wave numbers, which would be probably just about beyond our ability to measure. So it looks like 3 lines grouped together. Why 3 instead of 2J plus 1? Because the positions of 2 and 1 and 0 are the same as minus 1 and minus 2. It goes as K squared. So basically, symmetric top is really not that bad until you put in the non-rigid part. When you put in the non-rigid part, now for the prolate versus the oblate, that just means down here that for a given value of K, there's all these possible values of J, ranging from 0 to 10. If K is 1, then the lowest value of J would be 1. So this is the way we show these things. These are the energy levels as functions of J and K for the prolate case and the oblate case. The only difference is these drift up and these drift down. So in principle, you can calculate all of these levels. You can decide if the spacings are negligible and calculate the spectrum. But in the limit of rigid rotor, it's really not that bad. When you go to a polyatomic molecule, we have to rethink how we do the partition functions. In the linear case for rotation, rotational constant, remember B and C are equal, and the partition function goes as KT over sigma HCB. Remember HC over K is that 1.44 that I told you about that converts B into units of temperature. So you get temperature divided by HC over K times B, 1.44 times B. And then this is the symmetry factor. So if it's a homonuclear molecule like nitrogen, sigma is 2 because you can't distinguish it when I turn it around. But when I go to the symmetric top, I have to be careful. Now I have 3 axes of rotation. And the partition function changes. There's basically a square root of t for each of the 3 primary axes. So there's 2 axes here, I get a t. But in this case, now I have to worry about 3 axes, 3 rotations, so I have t to the 3 halves. It still depends upon B, but now it depends on A and B, whereas over here it was just B. So basically, all of these will have t to the 3 halves, but they'll have slightly different dependencies. Here we have to worry about A, B, and C. Remember, those are just the inverse of the moment of inertia. Rotational constant for each coordinate. Since these are spherical, it's B cubed. Since this symmetric top, B and C are equal, I can write it as AB squared. So if we look at these molecules that we might know something about, here's our CO2 molecule. Sigma is 2 because I can rotate it into 2 orientations that look the same from the side. It's a linear molecule. Symmetric top, here's a good example. So sigma is 3. I can rotate that ammonia 3 times and you can't tell the difference. CH4 is 12 times, it turns out. H2O is 2 times. So I can rotate that H2O into 2 positions. You cannot tell the difference. So that's how we use sigma. And here's these rotational constants. Again, just always H over 8 pi squared moment of inertia times C. So symmetric top, really not that bad as long as you think about it in the rigid rotor case. I'm just going to summarize. So linear case, diatomic and polyatomic, and symmetric top give very similar equal spacing at the rigid rotor level, that 2B. And you have to have high resolution if you want to detect these corrections or splittings. Why do we care about the spectra? So if you had a measurement of the spectra and the values of B or your values of A, B, and C, you can determine really the structure of the molecule, the lengths and the angles. So there's a link. This is our mechanical model. So there's a link between our mechanical model and the spectroscopic parameters B. And we use isotopes if we want to do some isolation of these parameters. Okay, so that's a very quick 15 or 20 minute overview of polyatomic rotations. What do? We classify molecules. Now we go to vibration. This is the one we really care about because we're really interested in Rovibrational spectra. These are the infrared spectra for which we can use laser absorption to make measurements in combustion problems. So in the rotational case, we establish the principal axes and the moments of inertia. In vibrational case, now we have to establish a number of vibrational modes. And there are a lot of different modes that are possible, and we have to categorize these things. They'll turn out into different types of bands. We'll call them parallel and perpendicular. We'll introduce fundamental overtones as we did before, but now we have something called combination of different bands. So I'm going to tell you about the different types of vibrational bands that you can see in spectra and their relative strengths. And then we'll finally deal with actual Rovibrational spectra. Linear, symmetric. So we start simple. Now here's a linear one, HCN. If I told you that the axis over here is energy increasing to the right, you would know where the P and the R are. Because remember, the R numbers are always bigger than the P numbers. That must be the R branch, that must be the P branch. They're almost the same height. They actually kind of look like the Boltzmann distribution of over rotation. But there's one new thing. What's this sharp peak here? Instead of a null gap, there's a peak. Well, that turns out to be one of the complications of a polyatomic. You can now have delta J of 0. So that's going to be the explanation for why we have that new feature. All right, so if we have an N-atom molecule, there's N atoms, it would take 3 N coordinates, x, y, z, to specify the instantaneous location of those nuclei. So it takes 3 N coordinates to specify that molecule at an instant in time. Typically what we do is we say, well, let's use 3 of those coordinates to specify the center. Let's use either 2 or 3 to specify the rotation. So if it's a stick, we only need 2 angular coordinates to specify that stick. If, on the other hand, it's not a stick, it takes 3 angular coordinates to specify the rotation. Now we subtract those numbers from 3n, and we say, therefore, there are 3n minus 5 vibrational coordinates. You might think of them as lengths. Vibrational coordinates in that molecule that we have to think about. Or 3n minus 6 in the case of the nonlinear molecule. So that's how many vibrational modes we have to worry about. And so as n goes up, this number goes up fast. How we identify or characterize these bands is through symmetry and energy. So this is like the Bible for how you keep track of the nomenclature for vibrational motions. We use nu typically to give us the name of the frequency name. Nu1 would be the highest frequency symmetric motion. Nu2 would be the second highest symmetric mode, until we finally run out of symmetric modes and we go into the asymmetric down here. Differently. So then we go to the highest frequency asymmetric. So depending upon how n is, and whether we're using 3n minus 5 or 3n minus 6, there will be some number of entries here, starting with the highest symmetric, progressing downward, then into the highest asymmetric, and so on. This looks kind of complicated. Typically, this is not a very long list. But that's the nomenclature that's used to denote which mode are we talking about. Are we talking about the Nu1 mode or the Nu2 mode? And that's how it's done. Now, there's some exceptions. There's always exceptions to rules. I don't think you need to be bothered about this. There's an exception for a special case that you won't run into very often. Let's look at some examples. Now, remember, we've got the number of modes to worry about. We've got to decide whether they're symmetric or asymmetric. And what counts is does the motion produce a change in the dipole moment along the a-axis or perpendicular? So there are parallel modes and perpendicular modes. Let's look at water. Water Here's the water molecule in a plane. Where's the unique axis? It's up through the oxygen atom in the plane. That's the one about which I can turn this thing and it looks the same. So that's the so-called unique or figure axis. There's the axis. So now we have to imagine how many modes are there that we have to worry about. There's 3 atoms. Times 3 is 9, minus 6 because it's nonlinear. There are 3 vibrational modes for water. 3. Now we have to decide what they are. If we have, for example, these hydrogen atoms acting in phase together along this axis, that would result in a dipole oscillation along the A-axis. That's a symmetric stretch. Then there's also a symmetric motion in which these things are bending. They're changing all around this angle. That's a symmetric motion, although it's a bending motion, not a stretch motion. And then there's the one where these things are oscillating different out of phase. That's called an asymmetric stretch. And each one of those has its own characteristic frequency that we could see in the spectrum. Turns out that this one is the biggest number, but it's still called nu 3 because our system is to start with nu 1, progress to nu 2, transition to the asymmetric, and now there's 3. So those are the frequencies and the motions of the vibrational motions of water. We can do something similar for CO2. There's again 3 atoms, so we have 9, but now we subtract 5 because it just takes 2 angles for that stick. We left 4. So there's 4 vibrational modes for CO2. If we first start with the symmetric ones, that's when the oxygen atoms are moving along this axis in phase with each other. So that's a symmetric stretch, it's called. But that does not produce a dipole moment, so it's not infrared active. It exists, but you can't see it. There's also an asymmetric stretch in which these end atoms are not in phase. That's called, and that's going to be the strongly active one. And then there's symmetric motions here, which produce our bending motions. So this is the B-axis, and the atoms are going this way or this way. And there's 2 of those. That's called degenerate. You can't distinguish between those 2. Their frequency is like 667. So remember, we have to worry about symmetry versus asymmetry, and we have to worry about parallel versus perpendicular. And why do we care? Because the selection rules change. Parallel is simpler than the perpendicular. So you start by counting the number of modes, and if typically you're going to look these numbers up and you're going to find them. But when they say we're measuring CO2 with the nu 3 mode, well, that's the strong one. So that's what they'll be talking about. So let's look at these modes of CO2. Here are the frequencies again that were on the past page, and this is the type. This one here's the perpendicular, here's the parallel. It's parallel, asymmetric stretch. It happens to be very strong infrared. Typically there'll be tables that will say S for strong, VS for very strong, NA for not active. Now there's the new column I put here, called the Raman column. So you can produce a Raman spectrum for these molecules too. The spectrum is weak. But there's a rule that says if for a symmetric molecule, if it's not IR active, it is Raman active. And if it's IR active, it's not Raman active for a symmetric molecule, like CO2. If I go to HCN, was an asymmetric molecule, I can go through the same strategy, strong, very strong, weak. But now the Raman are still there. Strong and weak, very strong and weak, weak and strong. So when it's asymmetric, you can have both IR and Raman. When it's a symmetric molecule, you have one or the other. So when we have our stick, what we have is the stick. And so if the atoms are going along the axis, those are going to be parallel. But if they're bending, they're perpendicular. And again, the reason we're going to care is that it affects the selection rules. Now, in molecules like this that have multiple levels, you have to recognize that there can be combination bands. And so the fundamental bands would be those in which the ith mode, nu sub I, that is written this way, nu sub I, means that there will be one change in nu. So delta V for a nu sub I is 1. That's called the fundamental. If we're talking about the overtone, it's written this way. It means there will be two quanta change. There will be a 2 quantum change in nu 1. So the quantum, this is the selection rule here too. For the ith mode, this will be much weaker than this one. So this is the notation. If someone says we're observing the 3 nu 1 mode, well, they're observing the second overtone for the ith mode. So I could be 1, 2, 3, 4, whatever. So this is a compact notation. Now in polyatomic molecules, it's a little more complicated because you can have a simultaneous change in 2 quantum numbers. So nu 1 plus nu 2 would mean that it's a transition in which nu 1 changes by 1 unit and nu 2 changes by 1 unit. This would mean that it's a quantum change in which there's a 2 quanta change in nu 1 and 1 and 2. So that's the very compact notation. Furthermore, it's possible to have difference bands in which nu 1 goes up by 1 and nu 2 goes down by 1. So as soon as you have polyatomics, you have to worry about these new combinations that take place. And it's all just compact notation that you get used to after a while. Now what about the vibrational partition function? So we're back to the simple harmonic oscillator approach, Q vibe. Remember we had, this is okay, there's multiple modes. Each mode has a partition function which is 1 over 1 minus e to the minus h nu over kt. So you simply multiply the product of each individual partition function. Each mode, so like the Born-Oppenheimer approximation, we assume things are uncoupled, they don't talk to each other. So the overall partition function for this multi-mode, modes might be, say, 3, is simply the product of the individual mode partition functions. Number of modes being the 3n minus 5 or the 3n minus 6. So here's the example for ammonia. Ammonia has 6 vibrational modes. So the overall partition function would be 1 minus e to the minus, I call this h nu over kt, minus 1, minus 1. Now we have to go to 2 because of the degeneracy, 2. So overall is 2, 2, 2, 4, 5, 6. Now we have, therefore, there's 4 frequencies, nu 1, nu 2, nu 3, nu 4. It's because these 2 are degenerate. Here's their frequencies, so you see this is the high number, therefore followed by this one. Then we go to the asymmetric and so on. And then we categorize them as whether they result in motions parallel to or perpendicular to the a-axis. So these happen to be symmetric stretch, symmetric bend, and so on. But when you get into these some of them are degenerate. That just means that there's 2 possible, there's a quantum number for each one of those similar motions. Okay, so the relative strength. Fundamental bands are much stronger than all of the others. If you have a harmonic molecule like carbon monoxide, the relative strength between these fundamentals and overtones is big. It might be 100 to 1. If you're close to this simple harmonic oscillator, overtone bands are nearly forbidden. They're there, but they're very weak. So a lot depends on the degree of anharmonicity. If it's highly anharmonic, turns out that ammonia is highly anharmonic. Now the strength between the fundamental and the overtone is about 10. So fundamental is about 10 times as strong. Overtone bands are less forbidden. In spectroscopy, we'll say the rule is it's forbidden. What it really means is it's kind of forbidden. It's not really forbidden. It's kind of, it's just discouraged, I guess. Now there's some exceptions. Molecules like resonances. If you have situations where there are degeneracies, that is where there are, and here's a good example. In CO2, the nu 2 motion has 667 wave numbers. It happens that 2 times nu 2 is 1334, is very, very close to nu 1. Therefore, nu 1 and nu 2 really like to talk to each other. Molecules can easily switch from having their energy in nu 1 to nu 2, go back and forth. How does that happen? In a small molecule like CO2, it only can happen when there's a collision. Collision happens, bangs it a little bit, the vibrational energy changes. If it's a big molecule, that's called intermolecular. If it's a big molecule, you can actually have all these motions taking place, and one limiting case is you can have intramolecular, and the vibrational energy can move around freely without a collision. So there's intermolecular and intramolecular. Small molecules needs a collision. Okay, so linear polyatomic molecules, the easy case. Remember, the energy is T, the sum of G and F. Now we have to go into the two cases. We've got parallel, and we're going to have perpendicular. This is now the linear molecule, parallel bands that's along the A-axis, of which there are two motions, symmetric and asymmetric. Selection rules, delta V is 1, delta J plus or minus 1. Everything is just like we've had before. Nothing's changed. So the parallel bands are just like a diatomic molecule. Example being HCN, nu 1 and nu 3 both. Not nu 1 for CO2 because that's symmetric. So now our energy level diagram would look like this. V double prime of 0, V double prime of 1, or V prime of 1. We can have either P and R. R is always the long one. Delta J is 1. Delta J is minus 1. And our pattern would look just like the ones we've seen before. P branch, R branch. That means the energy is going to the right, starting at R0, starting at P1 with a null gap. So everything is clean. This would be an example now for nu 3 mode of CO2. This is a transmission plot. So now here's the absorption, and then it goes back to 0. So away from the band, there's full transmission. This is really a null gap here. It's just that the resolution is not enough for us to see this. So that looks quite a bit like our. Okay, now another thing is, if you paid attention, you would know that in the R branch, the lines get closer and closer together. So this obviously is the R branch. This must be the P branch because the lines start getting more and more apart. So here's a case where the frequency goes this way. You would have noticed that if you remembered. R branch transitions are higher energy and have decreasing spacing due to the non-rigid effect. Now we go to the next level of complexity. What about perpendicular bands? We still are going to do this the same way. The selection rule for V is still the same, but now delta J is either plus or minus 1 or 0. So now for the first time, we have a Q branch. Remember the alphabet soup, O, P, Q, R, S. Delta J is 0 for the Q. So now we have down here, if we're level J, we can have an R branch, we can have a P branch, or we can also have a Q branch. So now the pattern looks like this, except there's a cluster of lines here in the null gap. So you can tell right away, are you looking at a perpendicular band or a parallel band? Because the perpendicular have the Q branch and the parallel band does not. If these B's are equal, if B upper and B lower are equal, this would be a single line. But the fact is the B's are not exactly equal. Remember, the B's are not exactly equal because of that alpha term in B that changes with V. So there's a slight spacing here that can be picked out in an experiment. Here'd be the example. So this is an example spectrum of the nu 2 bending mode. Remember, that's a perpendicular mode of HCN. So now you see this Q branch. And again, you know that this R branch is slightly bigger than the P, and it has decreasing spacing if you look close enough. There's stuff like this is usually due to some sort of impurity in the problem. Well, now let's go to the hard one. Go to the symmetric top, of which we have two types, prolate and oblate. Now remember, we are going to add G and F again, but now F depends on J and K. So we have our vibrational terms, and we have our rotational terms, where we now have A minus B K squared. So if A and B are equal, there'd be no term, and of course we're back to a stick. But now we have parallel bands. We always find the A-axis, and I find the center of mass, the A-axis, B and C. What is the selection rule? Delta V still stays 1. Delta J can now be plus or minus 1 or 0, no problem. Delta K is 0. So we're back to this. There's 2J plus 1 values of K, and in the limit of a rigid rotor, they're all going to be in the same location. But the intensity of this Q branch now, for delta J of 0, is going to depend on just how, on the values of the moments of inertia. So for example, if moment of inertia about A approaches 0, it's a stick. It's only when that moment of inertia about A gets bigger and bigger that we really see this behavior. Okay, so now, because there's so many possible combinations, we have to plot it in a simple way. So remember, for a given K, J can be K and bigger. So if K is 0, J can be range from 0 up. But there's 2 branches. So when you have K of 0, there'd be 2 branches, and you can have any value of J. When K is 1, you'll still have 2 branches, but you can only have J of 1 and higher, and so on. So if you plot them this way, you can see that now you add up the spectrum, and it'll look like this. The limit that this is nearly a stick, it reverts back to what we've seen before. But depending on how non-rigid we allow this to be, these terms, the lines begin to split a little bit. So you can understand this at least conceptually. Now this is this thing here. The splitting, that is the separation of some of these lines, depends on the magnitude of this difference. A and B are equal, there's no difference. But when the A and B gets, as that A gets bigger and bigger, meaning a declining value of, when the difference gets bigger, we see bigger differences. Okay, I didn't say that very well. So you can see splittings if you have a high resolution spectrometer. Some of the examples I've shown you so far didn't have enough resolution to really show this to you. There's a special case here. When K is 0, you go back to linear. So there's some simplifications. K cannot exceed J. Okay, here's an example. When I show you these examples, these were recorded on some sort of an instrument. It wasn't a laser. And so the resolution isn't good enough to see everything you'd like to see. But again, this is transmission, so absorption is going down. The R branch here, therefore, and the P branch, you can see the structure in the P branch. You cannot see it in the R, and here's the Q branch. So really, symmetric top isn't really that bad. Linear molecules, linear polyatomics aren't that bad. Symmetric tops aren't that bad. It's just that they have Q branches. Another example here. This is methyl iodide showing P, Q, and R. Now it's absorbance instead of transmission. Immediately, again, you can tell. As soon as you see the structure, that's the P branch. As soon as you see the taller one, that's the R branch. And there's the Q branch. And if you looked at the height of the Q branch, you begin to know something about how close is it to a stick versus a symmetric top. There are some equations you can write for the specific positions of the lines for the R branch, P branch, and the Q branch. Delta J of 1, delta K plus or minus 1. Remember, you can have plus or minus 1. Delta J is 1, therefore that's the R branch, but delta K can be plus or minus 1. Now, and now there's the expression. So everything always hinges on delta A minus B, but now also on, okay, so I didn't make this clear. When we did the symmetric tops, there's the parallel, which is pretty simple. When you go to the perpendicular, you have one more level of complexity, and that's why we begin to see this complication here. The same sort of thing, you can plot these individual things for different individual values of K, and they allow J's. You can add up all these lines and then plot it this way, and then add them all up. And so it's increasingly complicated as you go from parallel to perpendicular. It's increasingly complicated when you increase the number of modes. And it's increasingly complicated when you raise the temperature, because you can now have hot bands from transitions from excited states. So a lot just hinges on the properties of the molecule and the temperature. I think this is about it. Now we have a case of symmetric top perpendicular. That's the most complicated one, but a high resolution spectrum here. We picked a molecule, methyl chloride, which shows this, some of the structure. Okay, that's a lot to digest. That's a lot to digest. But what I've shown you is diatomics yesterday, polyatomics today. Why do we care? Because we care about doing, say, CO2, water. We care about detecting these triatomics and combustion problems using infrared light. That means Rovibrational spectra. I think I'm going too fast, maybe. So how about some questions? going roughly twice the speed that I give the lectures at Stanford, but compressed. So 3 lectures is 1 week. So 3 lectures, which was yesterday, was 2 weeks of real time at Stanford. So it's kind of, therefore, it's a lot to take in. But you know, it's like any subject where you learn. You read it more. You can keep reading it over and over, and you learn every time. So many things I want you to see the big picture, and then you can home in on what interests you. So we've talked about. Let me say something. I'll come back to your question. We've talked about mostly line positions. What's the practical application that we care about? We'd like to use absorption of light or fluorescence, laser-induced fluorescence, to detect the gas, concentration of the gas, pressure, temperature, velocity. So eventually, we want to look at the absorption or emission of light to characterize the gas. So far, we just talked about line positions. So we have to transition to line strengths and how we relate line strength to the absorption coefficient. Then we'll talk about line shapes. So in the next hour, we're going to talk about how we think about spectral absorptivity. And that'll be done through what's called the equation of radiative transfer. And we're going to introduce something called the Einstein coefficients, which are the fundamental spectroscopic properties for the strength of absorption or emission. They're introduced with a theory called the Einstein theory. We'll relate that to line strengths and what's called radiative lifetime. So basically, in the next hour, we're going to kind of say we're introducing what I'll call line strengths. In the following hour, we'll talk about line shapes. And that'll set the stage for lots of examples. Okay, what question?
So a lot of these techniques.
Okay, so in a liquid, of course, what's happening is that we still have atoms and molecules, but they're bound. And so they aren't freely rotating. They're coupled. So there is spectra, but they're blended spectra. So they don't have the free. We think of gases as being able for these molecules to rotate and vibrate, and we don't worry about the collisions, which are intermittent. But if you're constantly having a collision, then you're bound, and you have to modify the rules. Basically, it means that the spectra get blended. So instead of seeing discrete structure, you'll see kind of a blended. Kind of like also when we go to big molecules like hydrocarbon fuels, it just looks like a blob. So I think the rule is, and that's in my reader. I don't know if it's in these notes, in my book. I believe the way that rule is stated, I think it's called the rule of mutual exclusion, I think is what it's called. So if you have a symmetric molecule, then a symmetric molecule, like CO2 is a symmetric molecule. If you have a symmetric molecule, then regardless of whether it's parallel or perpendicular, take the case of the symmetric molecule. If it's infrared active, it will not be Raman active. So for a symmetric molecule, if it's infrared active, it's not Raman. If it's not symmetric, you can have both, but it'll usually be that one's much stronger than the other. Why do you care? Well, for that CO2 nu-1 motion, which is the symmetric stretch, it's not infrared active. So how could you study it? You could use Raman. And it usually means it will be very strong. So if you're looking in the Raman spectrum, you would see strong signals for nu-1, but no absorption. And why is that, you might say? Well, it's because we learned, and I think I cover it. I'm not sure I cover it. The selection rule for Raman will be delta J of 2. When you go to Raman, things change. And when you go back to quantum mechanics, you can explain all this with quantum mechanics for why is there no delta J of 1 for Raman, and why is there no delta J of 2? So in rigid rotor case, delta J is 1, and not delta J of 2. But in the case of that's for linear excitation. That's for the allowed transitions for electric dipole motions. Anyway, I don't know if I got it in my notes. I can't remember right now. But it's a well-known fact. It's called the rule of mutual exclusion. That means that you can always study You can always study a molecule. Just a question of what method you may have to use. So the quantum states exist, you just may not be able to see them by emission. Another question? Any questions? Okay. So we're going to move kind of fast through this. Personally, I really like the next part. The next part is how do we derive these probabilities? What is meant by the Einstein coefficient? That's something you probably, unless you had spectroscopy, you'll never have seen this before. It's amazing that Einstein was so smart to figure all this stuff out. Okay, so I guess we'll take a break. Let's see, what's our schedule supposed to be? Maybe we can get a little ahead of schedule. It's 9:35. Probably we're supposed to resume at 10. What if we resume at before 10, get ahead of schedule? Is that okay? This is 9:36. How about we resume at 10 to 10? Is that okay? And we'll be ahead in case I get going slower in one of these next lectures.